Okay, now earlier in chapter 5, we determined whether or not a given set of points is collinear. Now, um, now there were some sets where you have the points to be collinear, other sets where they are not. And looking at items like whether you have scattered plots or points that are not quite fully in line with one another, so to speak, we can determine what is referred to as the least squares line or the least squares regression line. And this part, okay, we're looking at solving what is referred to as the least squares problem. And this will involve looking at the use of matrices, especially coefficient matrices and their transversals. And for the least squares problem, okay, you have a matrix A, and that's going to be the coefficient matrix. And from earlier, and we'll get back to this now, B, again, that was a matrix that consisted of the y coordinates, and X was the matrix that consisted of the coefficients. And we have in the problem, okay, so we have the transversal of A times the difference between AX and B is equal to 0. And looking at what we have upon distributing, okay, we have the transversal of A times AX minus the transversal of A times B is equal to 0. And then we can establish setting a one-to-one relation whereupon we have the products of what we have between the transversal A and AX is going to be equal to the product where we have multiplying the transversal of A times B. Again, B being the matrix consisting of the y values. And okay, now when we looked at a situation where we had the points not quite come out as a collinear set, like when we have 1, 4, 3, 10, and -2, -7, so kind of going back, if they were collinear, okay, they would comply with this version of what we have with the slope-intercept equation of a line where we have C naught plus C sub 1 times X. And again, whenever we had the ordered pairs at 1, 4, 3, 10, and -2, -7, we set up these equations where we had the coefficient matrix A consisted of 1, 1, 1, 3, 1, -2, and X, again, we have the vector consisting of the values of the coefficients where we have C naught and C sub 1. And again, B we have as the matrix consisting of the y values, where in this particular case we had 4, 10, and -7. And if the points were collinear, we would have that A times X is equal to B. And when we ran through the process, once again, we had an inconsistent system, so the points were not quite collinear. And when we got it to the reduced row echelon form, again, we had the bottom row at 0, 0, -2, and automatically had the system to be inconsistent. So there was no solution for C naught and C sub 1 where we could have that AX is equal to B, and thus deem these 3 points as being collinear. Now, in terms of trying to come up with the next best thing, and this is looking at determination of the least squares solution, that is, determine the equation of the line that is closest to all of those given points. So again, we have with the coefficient A, we have 1, 1, 1, 3, 1, -2. X we have in reference to C naught and C sub 1. And for matrix B with the y coordinates, we have 4, 10, and -7. And again, taking the transverse of A, okay, so we're transitioning from a 3 by 2 matrix to a 2 by 3. So interchanging the rows and the columns. Okay, so you have 1, 1, 1, 3, 1, -2, so go column by column, and the transverse of A times A, and that is going to be equal to what we have, and just kind of going back, okay, like early days looking at multiplying matrices, like just for the breakdown, you have the transverse of A times the first column of A, so you got like transverse of A times 1, 1, 1, and we have 1 times first column from the transverse plus 1 times the second column from the transverse, and you have plus 1 times the last column from the transverse. And we have the sum of the products we had at 3, 2, and then working with the transverse of A and multiplying the second column of A, so you had the transverse times the 3x1 matrix, again with 1, 3, and negative 2. So you have 1 times 1, 1, plus 3 times 1, 3, plus negative 2 times 1, negative 2. And adding up the products, we have 2 and 14. And piecing those together, it turns out that the product of the transverse of A and A, again, we have 3 and 2 for the first column, 2, 14 for the second and last column. And for what we have for the product of the transverse of A when multiplied by B, again, you have the transverse of A multiplied by 4, 10, negative 7 from B. Here we have 4 times 1, 1, plus 10 times 1, 3, plus negative 7 times 1, negative 2. And again, taking the sum of the products, we come out to 7 and 48. And again, just for the rewritten equation, where we have AX equal to B failing to come out as such and coming up with the least squares solution, translating AX equal to B to both sides of the equation being multiplied by the transverse of A and just carrying over. So you had the transverse of A times AX. Guess what? I had the transverse of A times A. So again, we have 3, 2, 2, 14. X, we have C0 and C1. And the transverse of A times B, we just determined to be 7 and 48. And writing as an augmented matrix. Okay, so we have top row we had 3, 2, 7. Bottom row we had 2, 14, 48. And putting in terms of the reduced row echelon form, we have 1, 0, 1 19th. And the bottom row we have 0, 1, 65 19ths. And the 1 19th and the 65 19ths will reference what we have for C0 and C sub 1. And so we have for the least squares regression line. Okay, we had the Y, we have at C0 plus C sub 1x, and that's going to be 1 19th plus 65 19ths of x. So the line that's going to be altogether closest to these 3 points, again, we have y is equal to 1 19th plus 65 19ths of x. And I plotted these points to labels. So you got 3, 10, 1, 4, negative 2, negative 7. And again, we have with the line running diagonally, that is the least squares line. And it's not going to pass through those points, but it is going to be the closest to all 3 points once you put the distances all together.